In this video we're going to learn how to find the derivative of an implicit function. We're going to start with a simple example, the function x squared plus y squared equals 9. So the graph of x squared plus y squared equals 9 is a circle. It's not really a function because the requirement for a function is that if we do the vertical line test, that vertical line only hits the graph in one point, and clearly that's not the case for all the vertical lines that pass through this circle in this range. So we could write this as two functions by solving it for y, and then what happens is we get these two square root functions. The positive one is on the top half of the circle and the negative one is on the bottom half of the circle. And using the chain rule, we can find the derivative on the top half of the circle and the derivative on the bottom half of the circle. So we're going to do that on the next slide. So using the chain rule, we bring the power down, we reduce that power by 1, we leave the 9 minus x squared in there, and then we multiply by the derivative of that, which is minus 2x. That's the inner prime. We do the same thing here. The only difference is it has a minus sign out front, and so we get almost the same thing. And now we want to write this just a little bit differently. So we have our derivative on the top half of the circle and our derivative on the bottom half of the circle. And let's do a little bit of analysis of the signs for this. When x is negative, the numerator is positive and the denominator is always positive. When x is positive, the numerator is negative and the denominator is positive. And we do the same thing down here. X negative, we get a negative over a positive, and when x is positive, we get a positive over a positive. So if we look at the signs of y prime, on the top half of the circle, the sign of the derivative moves from positive to negative, and on the bottom half of the circle it moves from negative to positive. And if we go back and look at our circle, we see that yes, this is increasing, decreasing, and this segment here is decreasing, and this segment here is increasing. But this was a lot of work. Isn't there an easier way to do this, starting with x squared plus y squared equals 9 and leaving it in that form? And the answer is yes. So let's see how to do that. So we're going to leave our function in its implicit form. That means we have not solved it for y. We're going to replace y with f of x, and then we're going to differentiate each term using the chain rule, since this is a composite function when we differentiate this term. So the derivative of the first term is 2x, the derivative of the next term by the chain rule, bring the 2 down, reduce the power to 1, leave the f of x in there, multiply by the derivative of the inner f prime, and then the derivative of the 9 is 0. And now we're going to go backwards. So note that we first changed y over to f of x. Now we're going to go back and we're going to change f of x back to y, and we're going to change our f prime of x to a notation that we haven't used before, y prime. So that allows us to rewrite the line above as 2x plus 2y, y prime equals 0. We can solve that for y prime 2y prime equals minus 2x, and then y prime becomes, in canceling out the 2 minus x over y. So we got this result, which looks quite a bit different than the result we got before. Let's see that they are actually the same. So this is what we had before, these two expressions for y prime on the top and bottom half of the circle. But note that on the top half of the circle, y was the square root of 9 minus x squared, and on the bottom half of the circle, y was minus 9 minus x squared square root. So replacing them, replacing the square root here with minus y and the square root in the bottom half with y, we get y prime equals, on the top half of the circle, minus x over minus y, or excuse me, I had that wrong. This should be positive y, and on the bottom half of the circle, minus y. And so on the top half of the circle we have minus x over y, and on the bottom half of the circle we also have minus x over y. And so we get the same thing as we have when we do this implicitly, but the implicit method is much faster, especially as we're going to see when we take out these intermediate steps that we have right here. So let's do another example to see how we do this implicit method. We actually want to generalize it a little bit and note that when we take a y to the n term, we're going to replace it or rewrite it as an f of x to the n term, and then when we differentiate that, we're going to get n f of x to the n minus 1 times f prime of x, which is by the chain rule, and then we're going to rewrite that as, back in the y notation, y to the n minus 1 y prime. And so note that this is very similar to the derivative of x to the n by the power rule is n x to the n minus 1. Oops, I forgot my n here. And the derivative of y to the n by this implicit rule is almost exactly the same. It is n y to the n minus 1, and we just have to tack on a y prime. Okay, so once more to be clear, we're going to take any term that is y to the n and effectively rewrite it as an f of x to the n. Then when we differentiate it, we bring the n down, reduce the n by 1, leave the f inside, multiply by its derivative, and rewrite that in the y notation like this. And so that shows us that the derivative of a y to the n term is very similar to the derivative of an x to the n term, both by the power rule. When we take the derivative of x to the n, we get n x to the n minus 1. When we take the derivative of y to the n, we get almost the same thing as with x to the n and y to the n minus n and y to the n minus 1, but then we have to tack on the y prime. That's the inner prime part. So let's apply this to a little bit more complex implicit function than the first one. Let's first notice that for this function we could not solve it for y if we wanted to. While we can factor a y squared out of these two terms, that doesn't allow us to solve it for y because we have a y term over here and we're not able to isolate the y. I'll try it a little bit here, but you'll see that it won't work. Right, there's no way to get this term over here with the 8y in it grouped underneath this so we can solve for y. So typically we're not able to solve an implicit function for y and that's why we have this other method of taking its derivative. So let's take the derivative of each term. Power rule on this gives 2x. Start with the power rule on the y term and get 2y, but then we tack on the y prime as required. We're taking the derivative of this term, we have to use the product rule. So we get the first times the derivative of the second, which is this, using the implicit rule, plus the derivative of the first times the second, and then we go over to the term on the right side and differentiate it, and the y goes to a y prime. So let's just tag what we did with the product rule. Now, our objective in finding y prime is that we have to isolate y prime. We're going to be able to do that. We're going to take this term, and this term, and make sure that they are all on the left side. And we're going to take all the terms that do not have a y prime in them and move them to the right side. So let's restructure the equation doing that, or having done that. So we can factor out the y prime from all of these three terms, and we're going to do that. And notice that I fixed this sign here. It should have been a plus sign. And then we can solve that for y prime. Okay, notice that I fixed a little error here. This should have been 2x squared y, and it's adjusted now. And so here we have our answer, y prime. A little bit of complicated algebra in getting there, but the differentiation rules for the differentiating the implicit function, I hope you'll agree, are not too difficult. It's just the power rule tacking on a y prime. So once more, just to review how this is related to what we learned before, if we have a term x to the n, its derivative is n x to the n minus 1. The power rule, if we have a term y to the n, its derivative still uses the power rule first, and y to the n minus 1, but because it is an implicit function, we have to take the derivative of the inside, and that is y prime. So we've actually covered all of the derivative rules at this point. Let's put them all together on one slide. So we started off with the power rule for the derivative of x to the n. That was bring the power down, reduce it by 1, and x to the n minus 1. The product rule for f times s, first times second, was first times the derivative of the second plus the derivative of the first times the second. The quotient rule, numerator over denominator, was denominator times the derivative of the numerator minus numerator times the derivative of the denominator, all divided by the denominator squared. The chain rule for a composite function, the outer of an inner, was the outer prime at the inner, and then multiplied by the derivative of the inner, and we noted that there isn't a derivative of the inner at that point. And then the implicit rule, which is really just an application of the chain rule for taking the derivative of y to the n, is just like the power rule, n y to the n minus 1, but then we multiply by y prime, the derivative of the inside. So there are our derivative rules, and in the rest of this chapter we look at applications of all of these rules.